Hi guys, it seems an interesting avenue that is worth further exploration, and I am sure we will see further exploration. Let us continue further. In the meantime, the publication of a brief history of time catapulted Hawking to cultural stardom and gave a fresh face to theoretical physics. He never seemed to mind. In front of the camera, Hawking played the character of Hawking. He seemed an anthropologist from the University of California, Berkeley, who courted controversy in it. She investigated the way the people around Hawking helped him build and maintain his public image. That public image undoubtedly made his life easier than it might otherwise have been. As Hawking's disease progressed, the technologies gladly provided increasingly complicated machines to allow him to communicate. This, in turn, let him continue doing the thing for which he should ultimately be remembered for his science. Stephen Hawking has done more to advance our understanding of gravitation than anyone since Einstein, Carroll says. He was a world-leading theoretical physicist, clearly the best in the world for his time among those working at the intersection of gravity and quantum mechanics. And he did it all in the face of terrible disease. He is an inspirational figure, and history will certainly remember him that way. Hawking's paradox. In 2012, four physicists at the University of California, Santa Barbara, Ahmed Ameri, Donald Marolf, Joseph Polchinski, and James Sully, known collectively by physicists as AMPS, shocked the physics community with the result of a thought experiment. When pairs of particles and antiparticles spawn near a black hole's event horizon, each pair shares a connection called entanglement. But what happens to this link and information it holds when one of the pair falls in, leaving its twin to become a particle of Hawking radiation? One school of thought holds that the information is preserved as the whole evaporates and that it is placed into stable correlation among these particles of Hawking radiation. But AMPS asks, what does it look like to observe inside and outside the black hole? Enter Alice and Bob. According to Bob, who remains outside the black hole, that particle has been separated from its antiparticle partner by the horizon. In order to preserve information, it must become entangled with another particle of Hawking radiation. But what is happening from the point of view of Alice, who falls into the black hole? General relativity says that for a free-falling observer, gravity disappears, so she doesn't see the event horizon. According to Alice, the particle in question remains entangled with an antiparticle partner because there is no horizon to separate them. The paradox is born. So who is right? Bob or Alice? If it is Bob, then Alice will not encounter empty space at the horizon as general relativity claims. Instead, she will be burned to a crisp by a wall of Hawking radiation, a firewall. If it is allies who is right, then information will be lost, breaking a fundamental rule of quantum mechanics. The fervent controversy surrounding Hawking's paradox reflects the stakes his work has raised in quantizing gravity, what gives, and how much, says Rafael Basso of the University of California, Berkeley. The answer awaits us in the theory of everything, falls door to the underworld. The most basic description of a black hole states that what goes in never comes out. Based on Einstein's general theory of relativity, which describes how gravity affects the cosmos, a black hole is so massive that anything crossing its edge or even horizon is pulled in and lost forever, even light. Then in the 1970s, Hawking discovered that black holes themselves can disappear thanks to the prediction of the quantum mechanics. Physicists think space is not a vacuum but is filled with so-called virtual particles that wink in and out of existence. These particles appear in pairs that are doomed to annihilate as soon as they come in contact with each other. But if a pair appears on either side of a black hole's event horizon, one gets swallowed and the other radiates away into space. The escaping radiation steals energy from the black hole as it departs, so that the black hole loses mass over time. It eventually evaporates out of existence. According to Hawking's calculations, the lingering radiation, the only trace of a vanished black hole, contains no useful information about how the black hole formed and what it ate. That is the problem for physicists hoping to unite relativity with the quantum mechanics, which most experts say prohibits information loss. In search of this reversibility, Hawking revisited his original calculations. At the time of proposed black hole radiation, mathematical theorems had painted black holes as a fairly featureless entities when reviewed from the outside. All that could be measured was a black hole's total mass and charge, as well as how fast it spun. We show that if you throw something at a black hole, it in right way, you can implant here, says theoretical physicist Andrew Strominger of Harvard University. He and his colleagues illustrate this with charged particles. Like energy, electric charge can neither be created nor destroyed, because charge must be conserved in the universe. Hawking and his co-authors suggest that charged particles crossing the event horizon could leave traces of themselves in space in the form of strange particles of light called soft photons that have no energy. These bizarre photons change the vacuum of space-time and allow it to preserve information about the original particles. Hawking and his colleagues proposed that altered vacuum might store information about three-dimensional objects on the black hole's surface, in the same way that a hologram acts as a 3D representation of a flat image. Whether the mathematics of general relativity allows that it quite stubble, says Lee Smolin, a theoretical physicist at the Perimeter Institute of Theoretical Physics. Smolin instead favors quantum explanation of black holes based on their centers instead of their edges, adding that he will be looking for the other experts to check the math on the new paper. No one has yet reported a mistake in the calculations, but concerns have begun to pop up that the theory is at best incomplete. Sabine Hossenfelder of the Nordic Institute of Theoretical Physics questions how much information the proposed software could encode. She also points out that the paper does not explain how the hairs, which would disappear with the black hole once it evaporated, would transfer their information to the radiation that remains. I am not at all convinced that the new idea proposed by Hawking, Perry, and Strominger solves the information loss problem. She writes on the blog Baker Reaction. But it seems an interesting avenue that is worth further exploration, and I am sure we will see further exploration. Thanking you very much. You listened eagerly, patiently, and took interest. Please like the video, share it, and subscribe it. Thanks again a lot.